Doug Littrell again. It's June 9th, afternoon, about 2:30 or so p.m. Made a video this morning. I've been thinking about showing this section of a print that I made in 2015 called Symmetry in Motion. It's about orbits. Did this a couple of years ago. Anyway, I wanted to show this section here. At the top there is basically, now those are drawn to scale. You've got 1566 Icarus, is that very elliptical orbit that comes all the way within Mercury's orbit. I think it's considered a Earth crosser and Mars crosser. I think it's orbital path. I think it's a very dangerous asteroid. Anyway, there you have that's not what I'm going to talk about, but there's Mercury's orbit. There's 1566 Icarus going way up and around. There's Venus's orbit, Earth's orbit, Mars orbit. Okay, the outer planets are not included in that drawing, but that's to scale. That's those ellipses, and some look like circles, particularly Venus. They're all drawn according to the way they really are in space. Just below that is an elliptical orbit with an eccentricity of 0.95. It's highly elliptical. You can see the red line with the arrow. That's the side where the arrow indicates the arrowhead indicates the direction the body is moving in its orbit. And the red line with the arrow is indicating when the body is accelerating. You can't hardly see, but there's a yellow dot for the sun way down near the red arrow. Now, this is how orbits really work. This is not relativity, okay? The next ellipse is not as eccentric. Has an eccentricity of 0.76. No, the first one was 0.92, sorry. Anyway, the sun in this 0.72 elliptical orbit, it's way over here. It's still very near one end. Not as much as the 0.92 ellipse, but the red arrow with the arrowhead is showing when the body is returning toward the sun and when it would be accelerating. It will be decelerating as it moves away from the sun. That's not indicated. You're supposed to just assume that or understand it. It's implied. The next one is a 0.09. It looks very circular, and the sun in that one is very close to the center. It's maybe off a diameter of that circle, that yellow circle representing the sun, something like that. And you can see what I thought would be, when in the orbit it would be accelerating. Now, its accelerating is not as intense as it is in the other two. The intensity of the acceleration is much higher in this orbit, the 0.92 eccentricity. which is not as intense in this one, but still intense. It's not intense at all, but there's some slight acceleration in this orbit. Now here's a circular orbit. There's no acceleration. Everything is balanced. It's being pulled toward the sun the entire time, but its momentum wants to carry it forward, and it's everything's balanced. In my system, orbital mechanics system, everything, all orbits, if allowed enough time, they would eventually make circular orbits. And as they draw closer and closer, that's what I've come up with. Now, that aspect may not be perfectly accurate. I think it's true most of the time, if it's not always true. I know there are a couple of basically asteroids orbiting Mars, and they have eccentric orbits. One in particular, it's pretty close in. There are other factors that can be involved. But anyway, in this print, the concept is that, let's see here. Okay, a body that's captured approaches, let's say, from this side. That's 1566 Icarus to scale. And the sun is to scale in this. It's down here. The size of the dot is to scale for that orbit. Anyway, these bodies would approach from here, let's say in this area, and they would be drawn and turned toward the sun. When they get at what will become their perihelion in the future as they orbit, they go on past, and if they have enough velocity, not as much mass, they will make an elliptical orbit, much like 1566 Icarus or one of these others in our solar planets in our solar system that are not nearly as elliptical. Anyway, the circular orbit, the idea with the circular orbit, and my equation talks about circular orbit mass, what it would take for a body when it approaches and finds its perihelion when it first comes near the sun, its nearest point to the sun when it first approaches. If it has more mass, if it has enough mass, it will turn more tightly because it's more attracted, and it will make a circular orbit. If it was extremely massive, it would probably make a centripetal path, which would be circular, but it would close in more dramatically. It's pretty orbits are pretty interesting in this respect, because the more velocity they gain when they're close to, say, the sun, the faster they go, because they're being pulled. They're much closer, and they're being pulled much more intensely. And so the closer they get, the tendency is that their momentum would want them to move back out or stay put. But I have been thinking that they all close in eventually, just like the Milky Way's spiral arms are pulled and close in, and then are captured by the Milky Way's central very large, massive black hole. Now, it may be that in solar systems that the sun or a star isn't attractive enough, it isn't massive enough to actually overcome and cause those bodies to spiral in or enter a centripetal path where they collide with the sun. That may very well indeed be the case. But what I've come up with for orbits is that they should at least close down into all of them, given enough time. I believe they would most generally are predominantly close down into circular orbits. And the idea is, with my equation, is if they have more mass when they're first captured, they could immediately enter a circular orbit if they have enough mass. And things in my equation are figured based on that. Let's see. See if I can read this to you. It reads, the equation reads, COC, circular orbit mass, divided by, this is a value I came up with. It's off a little bit because this has to work with asteroids, and I haven't got it to work with asteroids yet, but I think this is fairly close. COC, circular orbit circumference, it's basically its period, the distance of its period, or one complete orbit, were to have that body to have a circular orbit, that distance from the sun, it would have, if that body were close enough when it's captured and didn't have too much velocity, it would have its circular orbit circumference is what COC is talking about, divided by 11,200, those two combined, then squared, times orbital velocity, its orbital velocity squared, equals COM, which is circular orbit mass. And that circular orbit mass, those two, also equal BM. Now this is body mass. All that is that BM is body mass. B capital M. COM, the M is also that's talking about mass, means mass. Okay, so this equals BM plus, in parentheses, BM times the eccentricity squared times 23. Yeah. One more note on this regarding symmetry and motion, the sheet, the print. Okay. Let me clarify something that I mentioned just previous to this amendment. In the Milky Way, the spiral arms are already captured by, it would be analogous to the planets have been captured and orbit the sun. The spiral arms of the Milky Way are captured by the Milky Way's central black hole, very massive black hole. And stars and planets are being consumed, or being dissolved, torn down and dissolved, their particles into that black hole. Now, when you get too much feeding in, it feeds off, a lot of the material feeds off back into space, like that's been shown in drawings, and I think there are even photographs of that actually happening. I doubted that when I first saw it, but it makes perfect sense. They've got that right. They've got a lot of things right, actually. That's one of them. Anyway, when the body is consumed, I said just a moment ago, when it's captured, I didn't mean the word captured. Just like I didn't mean the word mass contrast when I really meant charge contrast in the part A of video number 9. This is going to be part B, simply because it's also on June 9th, and if I'm going to make a run of these, I'm going to make one every day and call it whatever day in June it is. And this is part B, even though it's not about the same subject matter as video number 9A, which I didn't call it A. I didn't put A in it, but this is video number 9B, about symmetry and motion, orbits, what I've been talking about. Anyway, sorry I say anyway all the time. Sorry I say okay all the time. I have to work on that. But the idea is that what I think is probably true is that when a body is captured by the sun, whether it makes an elliptical orbit or immediately makes a circular orbit, which is unlikely, but it can happen. The more elliptical orbits close down into circles. The sun has strong enough gravity to cause that. I think that's a good thing to think of in relation to orbits. So the orbits around a star. But a star does not have the attraction force that a black hole has. A black hole will make those orbits around it and these spiral arms, when these bodies get close enough to it, they do make centripetal paths, because they can take it to another level and bring those bodies in and then consume them. Okay, that's the point I wanted to finish with on this. I didn't make that clear enough in the first part of this video.